So this is going to be your 5 electromagnetic radiation practice problems. We're just going to run through these together, and hopefully these will help you try and figure each specific question out and kind of what it's asking. So your number one problem says that microwave ovens emit microwave energy with a wavelength of 12.9 centimeters, and we need to watch our units. What is the energy of exactly one photon of this microwave radiation? Well, if we're trying to figure out energy, we know that our energy equation has to be here. This is Planck's equation to tell the energy necessary in order to solve for one photon. So we don't know our energy. That's going to be our end goal. Our H is always the exact same, 6.626 times 10 to the negative 34th joules per second. And this is just Planck's constant, so it's not changing at all. And then finally, we have a frequency. Remember that frequencies are always measured in hertz. And we don't have anything up here that is measured in hertz. So what we need to do is we know now that we need to solve for a frequency first. Now, I am going to write our only other piece of information that I've given you for this, and that's that your wavelength is 12.9 centimeters. So what you need to do is you need to think, is there a way in which you can use this value to solve now for frequency? Well, the first thing that you should realize is that there's only one equation that you know of that has the ability to use both wavelength and frequency in the exact same problem. That equation is right here. Velocity equals wavelength times frequency. For all 5 of these problems, we're going to be using this equation like mad, but now you have the question, what in the world is the velocity of this wave? Now, this again is a main idea whenever solving with electromagnetic radiation of any type of EMR, so microwave, radio wave, gamma, X-ray, it does not matter. These are all forms of light. Again, EMR equals light. And every single form of light always has the exact same velocity. It's denoted by the letter c, and it means the speed of light, 3.0 times 10 to the 8th meters per second. So if this velocity always stays the same, instead of writing it like that, why don't I just write it like that? C equals wavelength times frequency. And I can do that for any one of these 5 problems, as long as I have some form of light. Then finally, my wavelength I know is 12.9 centimeters, and my frequency is my unknown. So if I want to rearrange now this equation, I'm going to take c divided by my wavelength, and I'm going to get my frequency. Now, that looks all fine and good, and if I start plugging it in, that shouldn't be a problem. But if you notice, my wavelength now is in centimeters, and the speed of light is in meters, meaning I cannot plug that in quite just yet. What I need to do is I need to convert, which is why it goes and it says watch your units up here. So if I want to convert centi into just meters by itself, I'm going to go and I'm going to multiply it by a conversion factor with centimeters on the bottom and meters on the top. And I know my prefix centi means 100, like cents in a dollar. Meaning that at the very, very end, I can go and I can take 12.9 divided by 100 to figure out my wavelength, 0.129 meters. That way, now my units match and I can plug it in. I'm going to go then and I'm going to say that my speed of light, 3.0 times 10 to the 8th meters per second, divided by my wavelength, 0.129 meters, is going to equal my frequency, which, if I plug it in, let's see what we get. So 3e to the 8th divided by 0.129, and ooh, that's a gross number. I got 232558139 hertz. Now, that is my calculator answer, meaning that the very, very first thing that I need to do is I need to do sig figs. And you need to be careful here. This number down at the bottom has 3 sig figs, and this number up at the top only has 2. But you cannot use this 2 for sig figs, and I want you to think why. The reason for this is that this number, this 3.0 times 10 to the 8th, this is a given. You did not measure this, the same as you did not measure Planck's constant. Your sig figs go off of what you are measuring, and they went and they measured this 12.9 centimeters, meaning you need 3 sig figs here. So 1, 2, 3, I'm going to draw my line, round up, and I'm going to get 2, 3, 3, and then how many zeros? 1, 2, 3, 4, 5, 6, 7 zeros at the end. 3, 4, 5, 6, 7 hertz. Now, that by itself, that's the right number, but I don't want to keep it as that. 7 zeros is too many. What I'm going to do is I'm going to go and I'm going to write it as 2.33 times 10. And if my decimal is here, then I skip 1, 2, 3, 4, 5, 6, 7, 8, 9 to the right, meaning it is a positive 9 because I am getting larger hertz. So if this is my frequency now, then the very, very last step is to go and to plug it into my energy formula. I'm going to say E equals H times F. Again, just rewriting it, making sure that all of my ducks are in a row. I'm going to write it as 6.626 times 10 to the negative 34th joules per second multiplied by my frequency, 2.33 times 10 to the 9th hertz. If I plug this in then, I'm going to get a very, very small number, 2.33 e to the 9th times 6.626 e negative 34th, with 3 sig figs, again for my frequency, should be 1.54 times 10 to the negative 24th joules. That is going to be my energy for problem number 1. Let's go on to problem number 2. Number 2 states that the yellow light given off by a sodium vapor lamp used for public lighting has a wavelength of 589 nanometers. What is the frequency of this radiation? So here's what I'm going to do. Again, I'm going to write that I have a wavelength of 589 nanometers, and I'm trying to find a frequency. Now, again, same thing. I'm going to need some sort of equation that has both wavelength and frequency, and if we look back, the only equation that has both wavelength and frequency in it is your velocity equation. I'm going to do the exact same thing, but I'm going to write it now just as your original value of c equals wavelength times frequency. Oh, come on, pen. Pen. There we go. No, not eraser. Pen. There we go. So we have c equals wavelength times frequency. And if I want my frequency by itself, I'm going to take c divided by my wavelength equals frequency. Fine. Let's start plugging in all of my knowns and unknowns. C again represents the velocity, the speed of light, and it's always the same exact thing. 3.0 times 10 to the 8th meters per second. And my wavelength, I have 589 nanometers. Now, you should notice these two units, the meters up here and the nanometers down at the bottom, these do not match, meaning I have to convert. What we are going to do is that I'm going to convert this 589 nanometers, and I want to convert it into meters. Just think of it again. 589, nano is 1 times 10 to the negative 9th, is just your value for how many meters are in 1 nanometer. So, ooh, I actually flipped that. The idea here is that I went, and I should have written my units first, because my values here, I need 1 nanometer down at the bottom, and that 1 times 10 to the negative 9th meters up at the top, so that my units cancel. That way, I have 589 times 10 to the negative 9th meters. That's all nanometers means. and it makes it so much easier then to work with it. So now all we need to do is we need to plug it in. So we have 3.0 times 10 to the 8th meters per second divided by 589 times 10 to the negative 9th meters, and we want to figure out the frequency. So plug it in with me again, same thing, 3e8 divided by 589 e negative 9 equals 5.09337 e14. So 5.09337 times 10 to the 14th hertz. But now we, as always, need to take our sig figs. We have 3 sig figs from my wavelength, and the wavelength is the only measurement here in this problem, meaning we need 1, 2, 3 sig figs, and since it's after the decimal, I just chop it off. So I have 5.09 times 10 to the 14th hertz. It's going to be my final problem answer for my frequency. Let's keep on going. Number 3 goes, number 3 is the 2-part. All right, blue color of the sky results from the scattering. It's called Rayleigh scattering, actually, of sunlight by air molecules. The blue light has a frequency of about 7.8 times 10 to the 14th hertz. I want to first calculate the wavelength in nanometers associated with that radiation, and I want to calculate the energy in joules of a single photon. So let's do it here. I'm going to call this part A and this part B. For part A, what I'm wanting to do is I'm wanting to figure out wavelength. And again, if I have a frequency of 7.8 times 10 to the 14th hertz, the only equation that has both a wavelength and frequency here is, you've guessed it, the same exact velocity equation. I told you, you're going to be using it for almost every single one here. C equals wavelength times frequency. C divided by frequency equals wavelength. Rearranging it here, and let's plug it in. 3.0 times 10 to the 8th meters per second divided by frequency, 7.8 times 10 to the 14th hertz. And I'm, in the very, very end, going to get my value. So let's do it together. 3e8 divided by 7.8 e14. I get a calculator value of 3.846. I'll ignore that. 153, I bet that's enough, times 10 to the negative 7th meters. And I need sig figs here. Doesn't matter because it's a given. Here I have 2, meaning I need 2 sig figs of 3.8 times 10 to the negative 7th meters is going to be my wavelength. Okay, there's part A. It's not bad. Let's do part B. Part B is asking what is the energy in joules of a single photon associated with this frequency. The only equation that you know for energy is here. E equals h times f. If this is your equation, you know the frequency. The frequency's right here. All you got to do is you got to plug it in. E equals, h is the same, 6.626 times 10 to the negative 34th joules per second, multiplied by your frequency, 7.8 times 10 to the 14th hertz. And in the end, you get your energy. So, again, 6.626 e negative 34 times 7.8 e14 equals 5.168. 5.168 times 10 to the negative 19th joules. 2 sig figs then for my 7.8 again will give me a 5.2 times 10 to the negative 19th joules. There you go. So 2-parter, you got your wavelength, you got your energy, set, boom. Let's move on to number 4. Number 4 is the one that always goes and trips up students. And it says calculate not the energy or the wavelength. It says calculate the number of photons having a wavelength of 10 times 10 to the negative 6 meters required to produce 1,000 joules of energy. So Here's the idea that you need to know. First off, this equation, E equals h times F, this equation is only used for one photon, meaning that I cannot plug in this energy as this 1,000 joules. What I need to do is I need to solve how much energy one photon has, then divide this energy by that energy, and I will get my number of photons. So here's kind of the game plan. If I solve first for the energy of one photon, and then I go and I say, if I have the energy of one photon, I take that 1,000 joules divided by that number, whatever it is, and I will equal my number of photons. That's the idea here for this problem, which is why I need to first solve for this equation. So let's do that. If I have E equals h times F, again, I don't have my frequency here. The only thing that I have is going to be my wavelength of 10.0 times 10 to the negative 6 meters. Meaning that if I want to solve then for my frequency, you know the equation, C equals wavelength times frequency. C divided by wavelength equals frequency. I just rearrange in order to solve for that value. Let's plug it in. I'm going to go in and I'm going to say 3.0 times 10 to the 8th, not negative 8th. Oh gosh. All right, eraser, because that's going to mess me up even if I keep that. Of 10 to the 8th meters per second. Again, the speed of light, that is always the same. And I divide that now by my wavelength in meters, 10.0 is 10 to the negative 6 meters. Then I'm going to get my frequency. Whenever you plug it in with me, of 3e to the 8th divided by 10.0 e to the negative 6, I get a frequency of 3e13, and I need 3 sig figs here. So 3.00 times 10 to the 13th hertz is going to be my frequency. Then let's use it to plug it into Planck's formula. So E equals Planck's constant, 6.626 times 10 to the negative 34th joules per second, multiplied by my frequency, 3.00 times 10 to the 13th hertz. And we solve for the energy necessary for one photon. And I got, 1.9878 e negative 20. Well, that's gross, but I need 3 sig figs, so I'm going to say 1.9878 times 10 to the negative 20th joules is what I started out with. If I need 3 sig figs, 1, 2, 3, then this 7 rounds up, and I'm going to get 1.99 times 10 to the negative 20th joules is the energy necessary for one photon. So now I need to take my number of photons by doing this equation, 1,000 joules divided by my energy. So that's exactly what I'm going to do. I'm going to do 1,000 joules divided by 1.99 times 10 to the negative 20th joules. The joules will cancel. And if I do this correctly, of 1,000, I plugged in 100, 1,000 divided by 1.99 e negative 20, I'm going to get some gigantic number. Oh my gosh, yeah. Okay, so 5.025125, I bet that's enough, times 10 to the 22nd. And if I want sig figs, again, 3 sig figs, so 1, 2, 3, that 5 rounds up that 2, I should have 5.03 times 10 to the 22nd. And if I really want to label for it, I'm going to say photons necessary in order to produce that 1,000 joules. Okay, here's problem 4. One left. Let's do problem 5. Calculate the energy and frequency of a red light having a wavelength of 6.80 times 10 to the negative 7th meters. Well, sounds very, very simple. If you've been following along, same thing, E equals h times f. Let's solve then for my frequency. I'm going to skip some steps and I'm going to say just this, c equals wavelength times frequency. I know c divided by wavelength equals my frequency. C is 3.0 times 10 to the 8th meters per second divided by my wavelength, 6.80 times 10 to the negative 7th meters. So I get a frequency then of, let's see, 3e8 divided by 6.80 e negative 7. I get a calculator value of 4.411764 times 10 to the 14th hertz, but I only need 3 sig figs here, so 1, 2, 3 should be 4.41 times 10 to the 14th hertz for my frequency. Okay, there's part 1. Let's plug it in the second. E equals h times f. My Planck's constant is 6.626 times 10 to the negative 34th joules per second multiplied by my frequency, 4.41 times 10 to the 14th hertz. Oh, no, 14th hertz. And I am going to get my energy. So 6.626 e negative 34th times 4.41 e to the 14th equals 2.922066 times 10 to the negative 19. So 2.922066 times 10 to the negative 19th joules with 3 sig figs again, because this is a constant, it's a given, equals 2.92 times 10 to the negative 19th joules. There is your energy, there is your frequency, and that's problem number 5. And that concludes it. So, as always, please let me know if you got any questions. If not, then I will keep on going. Have a great night, everyone.